So, we now begin module 2 of lecture 4. So, this is the last class of scheduling algorithms we will study in the resource constraint scheduling approaches, and this will be heuristic fast solution approach. So, most of the heuristic fast solution approaches are based on the list based scheduling strategies. Now, this is a heuristic strategy as we said, and hence the solutions are bound to be suboptimal in most cases. However, as we said that because the optimal solution is highly time consuming to obtain, many a times we have to resort to such heuristic list based solution strategies. And therefore, list based scheduling is one of the most popular scheduling methods that we have, and we can consider this list based scheduling strategy as a generalization of the ASAP scheduling strategy, since it produces the same result as the ASAP scheduling strategy in the absence of resource constraints. However, if you do have resource constraints, it will not be the same obviously. So, what is the basic idea on which list based scheduling works? It maintains a priority list of ready nodes. During each iteration, we try to use up all resources in that state by scheduling operations at the head of the list. For conflicts, the operator with higher priority will be scheduled first. So, we have a priority list of ready nodes. That means, firstly we need to obtain a priority among the ready nodes, which is more important than the other. We have to obtain relative importance values among the operations. Now, we will schedule the highest priority operations at each time step to what? To the available resources that I have at that time step. All the resources may not be available at that time step, whatever resources are available. And if I have a ready to schedule set of independent nodes, the most important nodes will be given to the available resources. So, this is how we proceed, and finally schedule all resources. This is the basic strategy. So, now we will come to the algorithm. So, how does list scheduling proceed? It proceeds time step by time step. So, L denotes the time step and we proceed with time step 1. Let us say that I have k types of resources 1, 2 dot dot up to nr. Nr types of resources, k equals to 1, 2 dot dot up to nr. Now, what is the first thing to do at each time step? At each time step for each type of resource, the first thing to do is to obtain candidate operations, and then also determine unfinished operations at time step L. So, what does ULK determine? What does ULK tell me? ULK here, ULK gives me the number of ready to schedule operations of type K at time step L. Similarly, what does TLK tell me? TLK tells me the number of unfinished operations at time step L of type K. Why is this TLK coming here? TLK is coming here because this generalized scheduling strategy assumes that resources can have more than one unit delay. The delay can be higher than 1. Therefore, at a given time step there could be a few operations that are unfinished. Hence, what is the next step? The next step is to select SK, a subset of ULK. So, I can schedule at most ULK of the operations because ULK operations are only ready. Now, I cannot schedule all of them because I have resource constraints, and therefore, I will select a subset SK of these ULK operations such that SK plus TLK is less than equals to AK. So, AK is what? The number of resources that I have of type K. TLK is the number of unfinished operations. Now, therefore, how many resources are in total available at this time? AK minus TLK. Now, I can choose less than equals to AK minus TLK resources to schedule the ready to schedule operations at time step L, that is Sk. So, schedule Sk operations in time step L by setting Ti equals to L for our operation I such that Vi belongs to Sk and Sk is less than Ak. How has Sk been obtained? Through a priority function that we will look at. There could be various priority functions, and based on the types of priority functions, the complexity and the types of list scheduling algorithms vary. However, whatever it is, currently what we are considering is that we have chosen a set Sk of unfinished operations from ULK, and we have to therefore assign time steps to these operations, and that is done by Ti equals to L and where I for all I where Vi belongs to Sk. Now, if these operations have been allocated at time step L, then we need to increment time. We increment time and do again the same thing and continue until all operations have been scheduled. So, we increment time and again for each resource type find out the number of ready to schedule operations that have now become available. Because I have incremented time, some of the operations that has already been allocated already been allocated for scheduling may have completed, and then we can have a new set of operations in ULK, and therefore scheduling will continue in this fashion, and we will continue until all operations have been scheduled. Now, we will take an example. In this example, the figure on the top, this figure gives me a set of priority values on each node. The index number of the node is given on the top left corner of each node. So, this one here, this 2 here, these are the index number of the operation IDs of the corresponding to the operations. The values on the left bottom corner, this 4 tells me the priority values corresponding to these operations. Before the list scheduling algorithm, as we said, that we will have a labeling of priority values attached to each node. This is one arbitrary labeling that has been attached to this set of nodes. Now, how has this been obtained? This priority value has been obtained as follows. This gives me the weight of the path starting from the current node to the sync node. So, for example, let us consider operation 5. The weight of this path is 1, because the distance, there is only one node, there is only one edge that takes it from this node to the sync node. Again, the weight of node 4 is 2, because the length of the path from the node 4 to the sync node is 2. The weight of 3, and because each of these nodes have unit delay, so the length of the path also gives me the weight of the path, and that also gives me the priority, and hence the label or the priority of, let us say, operation 3 is what is 3, because that is the distance from node 3 to the sync node. For nodes 1 and 2, similarly the priority value is 4. For node 6, the priority value is 3, because see the length of the path from node 6 to the sync node is 3. The priority value of node 7 is 2, because the length of the path from node 7 to the sync node is 2. This is how we have obtained a priority labeling of all nodes in the operation constraints graph. Now, here we again assume that, let us say, we have 2 multipliers, A1 equals to 2 multipliers and A2 equals to 2 ALUs that are available to me. Now, given these priority levels, we will operate, we will progress time step by time step. list scheduling progresses time step by time step, and at each time step the first thing we will operate for each operation type. So, let us say we first look for multiplication, k equals to 1 is multiplication. So, how many multiplication operations do I have? I have V1, V2, V6 and V8. Now, I can allocate at most 2 because I have 2 multipliers. Now, what are selected? V1 and V2 are selected. Why? Because V1 and V2 have the maximal label. So, the value of the table is for both 1 and 2, V1 and V2 is 4. That for V6 and V8, the other two available nodes at time step 1 of multiplication type are 3 and 2, and hence V1 and V2 have higher priority with respect to V6 and V8, and therefore, at time step 1 V1 and V2 are selected. Similarly, for the second resource type ALU, what do we have? We only have V10 that is available, and hence the operation V10 will be allocated to one ALU resource. At time step 2, similarly what will happen? I have V3, V6, V8. So, V1 and V2 has already been scheduled. Now, because V1 and V2 has been scheduled, V3 becomes available because its precedence constraints are now satisfied, and therefore, among V3, V6, V8 we take V3 and V6. Why? Because V3 has a label of 3 and V6 has also a label of 3, while V8 has a label of 2. So, the higher priority nodes are V3 and V6 with respect to V8, and hence they are scheduled. For the ALU operation, what do we have? We have only V11 that is available. V10 has been scheduled. V11 is the only operation that is available currently, that is ready to be scheduled, and hence it is allocated to the adder resource, and scheduling proceeds likewise, and the final schedule has been shown here. With this, we come to the end of module 2 of lecture 4.